If the net force is constant, the acceleration is constant, okay? The first option says constant velocity. If it is constant velocity, the acceleration will be 0. So this is not true. Constant acceleration is option B. So that is our answer. The answer to 1.1 is B. Constant force, constant acceleration, not constant velocity. Constant velocity implies that the acceleration is 0, which is not correct. 1.2, a crate of mass m is stationary on a plane inclined at an angle theta with a horizontal. Which one of the following statements regarding the magnitude of the frictional force acting on the object is correct? So the crate is stationary, right? If we draw a free body diagram for m, we're going to have the frictional force, not the frictional force, but Fg parallel. We're going to have Fg parallel pushing down the object, but it is stationary. That means that frictional force is pushing it up the incline. We have the normal force and we have Fg perpendicular. Okay, so clearly you can see that Fg parallel is equals to the frictional force. That is why our object is stationary. Let's hear the stories. The magnitude of the frictional force acting on the crate is, the first option, equal to the component of the weight of the crate which is parallel to the plane. We don't have to go any further. That is what we are saying. So the answer to 1.2 is A. Okay. 1.3. 1.3 says a ball is projected vertically upwards from the top edge of a building. Points P, Q, R, and S represent different positions during the motion of the ball, as shown in the diagram below. Ignore the effects of air resistance. Between which 2 points will the ball undergo the greatest change in kinetic energy? So the change in kinetic energy, EK final minus EK initial. Let's take a look at our situations. Okay, we have P and S as one of the possible options. Okay, at S we have some Vx. Okay, let's say Vs. Yeah, let's say Vs and not Vx. Okay, so at S we have some Vs. At P we have some Vp. Okay, and then let's take a look at P and R. At P, we have VP. At R, we also have VP. Okay? It's just that with a negative sign or a positive sign, depending on which direction you take a switch. But the magnitude of the velocity at P is equal to the magnitude of the velocity at R. Okay? So P and R, the change in kinetic energy there is actually 0 between P and R. So this cannot be the correct option. The answer, P and R, the change in kinetic energy is 0. Let's move to R and S. Okay, the change in kinetic energy between P and S is the same as the change in kinetic energy between R and S, because Vp, the velocity of at P, is equal to the velocity of at R, right? So A and C cannot be the correct answers at the same time, right? We cannot have A being correct and C being correct. So clearly they all have to be wrong. The correct answer is actually D, okay? But we can make sense of that. We can justify why D is the correct answer. At Q, that is the maximum height. So the kinetic energy at Q is 0. But at S, we have some Vs, okay? So Vs minus 0 will be greater than Vs minus Vp, okay? That makes sense. Right, so the answer to 1.3 is actually D. 1.4, let's hear the stories. I think I've seen this before. A ball is dropped from height h and strikes the floor with momentum p. The ball is then dropped from a height a half h. Ignore the effects of air friction. Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from height a half h? Okay, so we know that p, we need m and v. M is not changing. What is changing is v. So we need to figure out how v is changing as a function of h. In order to do that, we can say that Vf squared is equal to Vi squared plus 2a delta y. All right. This is our formula of choice because it's been dropped, so Vi is 0. The only thing that is affecting Vf is delta y. Okay. So Vf will be equal to the square root of 2a delta y. Right. Vi is 0. So let's look at our case where the height is h. In our case where the height is h, we're going to have P being equals to M multiplied by 2AH, right? Looking at the case where the height is a half h, we're going to have P being equals to M multiplied by 2A multiplied by h divided by 2. 2 and 2 cancels out, so we have M multiplied by the square root of AH. Okay, let's look at the case where the height is h. We're going to have P being equals to the square root of 2 multiplied by M multiplied by AH. Okay, so as you can see, the momentum when the object is being dropped from a height h, let's call this momentum px, will be equals to px divided by square root of 2. If you divide this by square root of 2, you get the momentum when the ball is dropped from a height of h divided by 2. So the answer to 1.4 is B because of that. Okay, 1.5. 1.5, a box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Which of the following combinations of forces do work on the box? Okay, so obviously P is not doing any work because the object is moving horizontally. The angle between P and the movement of the box is gonna be 90 degrees. If it is 90 degrees, cos of 90 is 0, so it's not doing any work. Same is true with R. The angle is going to be 90 or 270 depending on whether you move clockwise or anti, right? But the work done by P and R is 0. So the only forces that are doing work is S and Q. Okay, so which option says S and Q? That is B. So the answer to 1.5 is B. 1.6, a train moving at a constant velocity towards a stationary listener emits sound waves at constant frequency. Which one of the following statements about the sound waves observed by the listener is correct? So the train is moving towards, if the train is moving towards higher frequency, lower wavelength. Let's look at A. Frequency is higher than the emitted frequency. We don't have to go any further. The answer is A. Yeah. Okay. 1.7. Yeah, that is conceptual. We should be getting that one. 1.7. Q and R are small spheres suspended by light insulated strings. When a negatively charged rod is brought close to sphere Q is repelled. Okay, when the negatively charged rod is brought close to sphere R is attracted. Which one of the following combinations below can be possible for the nature of the charges on sphere Q and R? Okay, if you look at option A, we have negative and negative. So Q and R cannot be negative, and then they act differently when they are brought close to the rod, right? They should act in the same way. So this is not correct. A cannot be correct, right? They cannot be all negative and act differently around the same charge. B says Q is positive. If Q is positive, it should not move away. It should move close. Opposite charges attract. So this cannot be correct. Let's take a look at C. C says neutral. C cannot be correct. Why? Because if you have a negative and a neutral, they attract. If you have a negative and a positive, they attract. So the mere fact that it is moving away, it means that it is not neutral. If it was neutral, it was going to move towards the rod. So C is not correct. Obviously, D should be correct. Okay, so let's look at the other side. The other side, it says R is neutral and is being attracted by the rod. So that makes sense. 1.7, the answer is D. 1.8, in 1.8, 4 voltmeters V1 and V2, V2, V3, and V4 are connected in a circuit, as shown in the diagram below. Which voltmeter will have the same reading as voltmeter V1 when the switch is open? Let's take a look at V1. V1 is reading the EMF, right? When the switch is open, it's connected across the ends of the battery because there's no current flow in here when that switch is open. Okay, the current is going to try going through the voltmeter, but it can't because it has very high resistance. So V1 is reading the EMF. Okay. Can V2 read the EMF? No, it cannot. It is not connected across the ends of the battery. The same is true with V4, right? But V3 is reading the EMF. So the answer to 1.8 is B. Okay. If you cannot see how this comes about, you can actually open a simulation online and set up this circuit and look at the reading on V1, V2, V3, and V4. The reading on V1 and V2 will be V1 and V3 will be the same. I mean, so the answer to 1.8 is actually B. 1.9. A split ring connects the coil of a generator to an external circuit. Which one of the following combinations below is correct for the magnitude and direction of the induced current in the external circuit? Magnitude of the induced current. Okay, the magnitude of the induced current changes. So we're looking at C and D. Okay, you know that we draw a graph where we have I on one side and time on the other side, and then it is going up until I max and goes down. So clearly the current that is induced changes. Okay, now let's talk about the direction of induced current in the external circuit. The direction of the induced current in the external circuit when you have a split ring is constant, right? In the external circuit. That is a keyword. In the external circuit, it is constant. So which option satisfies those two conditions? I think it is option C and not D. So the answer to 1.9 is C. 1.10 on the other hand, let's take a look. Where's 1.10? Oh, okay, yeah, it is. I was surprised. Light of visitable frequency is shown on the surface of a metal and electrons are ejected from the metal. Which one of the following is equal to the ratio of the work function to the threshold frequency of the metal? Okay, so what is work function divided by threshold frequency equals to? Is equals to Planck's constant, because if you cross multiply, work function is equals to Planck's constant multiplied by threshold frequency. Okay, so that is option A. The answer to 1.10 is A. State Newton's second law of motion inwards. So when a non-zero resultant force is applied on an object, the object will accelerate in the direction of the non-zero resultant force, with an acceleration that is directly proportional to the non-zero resultant force and inversely proportional to the mass of the object. That is Newton's second law, 2.1. Let's take a look at 2.2. Okay, so in 2.2, the kinetic frictional forces acting on block A and B are 5.88 newtons and 13.23 newtons respectively. Okay, so that of A is 5.88 and that of B is 13.23. And then the equation 2.2, we're supposed to draw a labeled free body diagram showing all the forces acting on block A. So let's go ahead and take a look at block A. Before we start thinking about anything, we have the weight, obviously. So there goes the weight. Block A is resting on a surface, so the surface will apply a normal force on the object. So we have the normal force in that direction. Okay, A and B are connected by a string, so there's a tension pointing in that direction up the incline. But there's kinetic frictional force which will be opposing the motion. So there we go. We have our kinetic frictional force. Okay, that is 2.2. The Muggle equation is 4, and we have 4 forces on our free body diagram. So we are quite convinced that we have done the correct thing. If the Muggle allocation is 4 and you have 3 forces on your free body diagram, you're probably doing something wrong. Okay, let's move to 2.3 and 2.3.1. In 2.3.1, we want to calculate the tension in the string. In 2.2, we have the free body diagram of object A, block A, right? So let me use block A again in 2.3.1. We want to find the tension force. As I always say, we start by saying F net is equals to MA all the time in question 2. This is Newton's second law. How you want to follow up this equation is by doing the following. Which force is pulling your object? It is the tension. So you want to say tension minus all the forces that are opposing. Okay? We have frictional force. So tension minus frictional force because it is opposing. Right? So we're going to have tension minus frictional force. But I want you to take a look at something. We have the weight of which we can resolve into FG parallel and FG perpendicular. So we have FG parallel that is also opposing the motion. So minus FG parallel. This is equals to MA. So what is the tension? The tension is what we are interested in. What is the kinetic frictional force of block A? It is given to us as 5.88 newtons. So we're going to have 5.88 minus FG parallel. FG parallel is just mg sine of theta, okay? Of which theta is 35 degrees. So we're going to have the mass of block A, 4 kgs, the gravitational acceleration, 9.8, cos, not cos, but sine. The parallel component on an inclined surface is sine. So we have sine of 35 being equals to MA. The mass is 4. Are we given the acceleration? If you take a look at your equation statement, you shall realize that the blocks now accelerate up the incline at 2 meters per second. So we have an acceleration of 2. Okay, so we're going to have the tension minus. So we have minus 5.88 minus 4 multiplied by 9.8 multiplied by sine of 35. If you put that in your calculator, you're going to get minus 28.3642 being equals to 4 multiplied by 2, which is 8. So the tension is just equals to 8 plus minus 28.3642, right? When minus 28 goes to the other side, it is going to be plus. So it's just 8 plus 28.3642. The tension is going to be 36.36 newtons. That is the tension on the rope, okay? 2.3.1. Let's take a look at 2.3.2. In 2.3.2, we're looking for the force F. The force F is applied on block B. So we cannot use block A to find the force F. We have to use block B, okay? Obviously, we can go ahead and say F net is equals to MA, go ahead and substitute. But let's draw the free body diagram first. I cannot do it without a free body diagram. I always have to draw a free body diagram first. Okay, how will that look like? We have the force which is applied. But on block B, the tension is opposing. So we have tension down the incline. We have the weight and we have the normal force. So that is the free body diagram for block B. There's no mark for this free body diagram, but I need it in order to answer the question. I cannot answer it without the free body diagram. Okay? If I use the same idea I used in 2.3.1, I'm going to say that F net is equals to MA. Which force is pulling our object? F. Which force is opposing? I'm missing something. There's a frictional force. Let's not forget that. Right. So the forces that are opposing, it is frictional force, it is tension, and it is FG parallel being equals to MA. Okay. So we're gonna have F, the frictional force, not the frictional force, but the applied force, minus the kinetic frictional force, which is 13.23, minus the tension, which is 36.36. So we have 36.36 minus FG parallel. FG parallel will be the mass, which is 9. So we have 9 multiplied by 9.8 multiplied by sine of 35. So that sine of 35. This is equals to MA. The mass is 9 and the acceleration is 2. Okay? So we're going to have the force minus 13.23 minus 36.36 minus 9 multiplied by 9.8 multiplied by sine of 35. I'm getting 100.1794. being equals to 18. So the force applied will be equals to 18 plus 100.1794. Okay, this is 118.1794 newtons. Right, that is the magnitude of force F 2.3.2. 2.4, let's hear the stories. In 2.4, the angle that the plane makes with the horizontal is now decreased. Okay, this angle is decreased now. What is the question saying? How will this change the kinetic frictional force acting on block A? Choose from increase, decrease, or remain the same. And then in the question that follows, we're supposed to explain our answer. Okay, so let's take a look at 2.4.2 first. Okay, so we want to figure out whether the kinetic frictional force is going to increase or decrease. Okay, so Fr is given by the coefficient multiplied by the normal force. The coefficient is dependent on the material, so it's not going to change. What about the normal force? The normal force is the mass multiplied by gravity multiplied by cos of theta. Okay, the coefficient is not changing, the mass is not changing, the gravitational acceleration is not changing. So what we're interested in here is the effect of cos of theta on the frictional force. The angle is decreasing, right? So let's see how that affects cos of theta if the angle is decreasing. We know that cos of 0 is equals to 1. Cos of 0 is equals to 1. What about cos of 20? Okay, let me put that in my calculator. Cos of 20 degrees, that is 0.94. Let me say cos of 35. Cos of 35 is equals to 0.82. So you can clearly see that when we decrease the size of the angle, when we decrease theta, cos of theta increases. So the frictional force is going to increase if we are decreasing the angle, right? As you can clearly see, as the angle decreases, cos of theta increases. The term free fall. So free fall is the motion of an object under the influence of gravity only, right? That is free fall. You start by saying the motion. If it was projectile, you would start by saying it is an object, so on and so on. That is the difference between free fall and projectile. Free fall is the motion of an object in which the only force acting is gravity, it's gravitational force. That is free fall. 3.1. Let's take a look at 3.2. We have to go through our question statement. So a ball of mass 0.5 kg is thrown vertically upwards from the top edge of a building which is 15.3 meters high. The ball reaches a maximum height of 5.89 meters above the top of the building. The ball strikes the ground and bounces vertically upwards, reaching a maximum height at point P, as we can clearly see. Okay. 3.2. Using only equations of motions, calculate the speed at which the ball was projected upwards. So we will consider the motion of the object from the time it is projected until the maximum height. If we only consider that part of the motion, then VI is what we would be interested in. VF will be equals to 0 meters per second, maximum height. Our acceleration, if we take up as positive, it will be negative. So we're going to have minus 9.8 meters per second squared. Do we have delta t? We don't, but we have delta y, which is equals to 5.89 meters. That is the displacement of the object from the time it is projected until maximum height. 5.89, not 5.89 plus 15.3. No, but 5.89. We're only considering the part of the motion from the time it is projected until maximum height. If we look at these equations and you want to find VI, not these equations, but if you look at these variables and you want to find VI, the equation to use is VF squared is equals to VI squared plus 2A delta Y. Okay, VF that is 0 squared, being equals to VI. VI is what we're interested in, multiplied by plus 2 multiplied by A, which is minus 9.8. Delta Y is 5.89. 0 squared is just 0, obviously. If we take VI squared to the left-hand side, we're going to get minus VI squared being equals to. So now I have 2 multiplied by 9.8 minus 9.8 multiplied by 5.89. That is minus 115.444. If I divide both sides by minus 1, I'm going to have VI squared being equals to 115.344. Now I need to take square roots on both sides. If I do that, let me just go ahead and do that. I'm going to have 10.74 meters per second. I was looking for the magnitude or the velocity. Let me take a look. The speed, okay, speed, we only need the magnitude. So that is the speed at which the object is projected upwards, 3.2, 3.3, 3.3.1. After the collision with the ground, the ball leaves the ground with a speed of 11.92 meters per second. Okay, let's hear the stories. The question: calculate the amount of energy lost by the ball during the collision with the ground. That is for 5 marks. Let's make sense of that. We want to find the amount of energy, of kinetic energy lost by the ball during the collision with the ground. Okay, so as the ball strikes the ground, it is striking the ground with some EK, right? Because it has a velocity. Its velocity is not 0. And then as it leaves the ground, it is also leaving the ground with some EK. So we want to find how much kinetic energy the object loses, the ball loses, when it is in contact with the ground. So we need to find EK as it strikes the ground, and we need to find EK as it leaves the ground. We need to find those two kinetic energies and find the difference between the two. The difference will be the kinetic energy that the object lost as it was in contact with the ground. So let's concentrate first on the kinetic energy as it strikes the ground. So we're looking at the kinetic energy as it strikes the ground. E is equals to EK, not just E, right? Because E can be inert. So EK is equals to a half mv squared. I need to write down this formula first before anything else. Now let's take a look. Do I have the velocity as the object strikes the ground? I don't. I only have the velocity as the object leaves the ground, but not as it strikes the ground. So I need to find the velocity as the object strikes the ground. Okay, let's go back to our sketch. Now we are considering the entire motion from the time it is projected until it strikes the ground. Okay, that is the motion we are considering now. Delta y for that motion is minus 15.3. The displacement is downwards. Okay, A obviously will be minus 9.8 meters per second squared. If we take upwards as positive, that is. What else do we have? We have VI from the equation above. VI is 10.74 upwards, so that is positive. Okay, I want to find VF, or the velocity as it strikes the ground. With these 4 variables, which equation can I use? Is VF squared is equals to VI squared plus 2A delta Y gonna work? Yeah, I think that can work. So let's go ahead and find the velocity as it strikes the ground using that equation. VF squared is equals to VI squared plus 2A delta Y. VF squared is what we're interested in. VF, not VF squared, but you know what I mean. And then VI, that is 10.74 squared plus 2 multiplied by A minus 9.8 multiplied by delta Y minus 15.3. So VF squared is equals to, okay, let me just go ahead and put that in my calculator. plus 2 multiplied by minus 9.8 multiplied by minus 15.3. I'm getting 415.2276. So VF is equals to. Now I just need to take square roots on both sides. If I do that, I'm getting 20. So I have 20.3771 meters per second downwards, right? This is downwards. Okay. So now that I have, this is the velocity as the object strikes the ground. Now that I have the velocity as the object strikes the ground, I can go ahead and substitute it on EK. So EK will be equals to a half m. The m, the mass of the object, that is 0.5. So I'm going to have 0.5 multiplied by the force. Not the force, but the velocity. What am I saying? The velocity is 20.3771 squared. Okay? This will be equals to. So let me go ahead and put that in my calculator. 0.5 multiplied by 20.3771 squared. Okay, I'm getting 103.8066 joules. This is the kinetic energy as the object strikes the ground. Okay, now let's look at the kinetic energy as it leaves the ground. As it leaves the ground, we're going to have EK being equals to a half. The mass is 0.5. The velocity as it leaves the ground, it is given to us 11.92. So that's what we need to substitute. 11.92 squared. Okay, now I just need to put that in my calculator. Okay, so 11.92, I'm getting 35.5216 joules. So this is the kinetic energy of the object as it leaves the ground. I want to find the amount of kinetic energy that is lost. So the amount of kinetic energy, so I can just say EK lost. EK lost. There is no formal way of writing this. EK loss will be EK that we started with as we are striking the ground. We have 103.8066 minus the kinetic energy as we are leaving the ground. Okay, so minus 35.5216. Is it 5216? Okay, I think it is 5216. Let me just go ahead and put that in my calculator. 103.8361 minus 35.5216. I'm getting 68.31 joules as the amount of kinetic energy that is lost. So this kinetic energy is converted to heat, is converted to sound and other form of energies, right? It is not disappearing. We know that it cannot disappear. It's just being converted from one form to another. That is 3.3.1. Quite an interesting question. It's the first time I see a question like this. Honestly, I've solved a lot of questions. It's the first time I'm seeing a question like this. But still, that doesn't mean you should get the question wrong because it's quite basic. You just needed to realize that, okay, I can find the kinetic energy as we strike the ground, the kinetic energy as we leave the ground, and then the difference will be the kinetic energy lost in contact with the ground. Anyway, 3.3.2. Let's take a look. 3.3.2. Time taken for the ball to reach point P after leaving the ground. Okay, we leave the ground with a velocity of 11.92 meters per second upwards. And then at point P, that is our maximum height after striking the ground. So VF should be equals to 0. Acceleration minus 9.8. If we're taking up as positive, we're interested in delta T. So I think this is quite easy to compute. VF is equals to VI plus A delta T. Vf is 0, Vi is 11.92 plus the acceleration minus 9.8 multiplied by delta t. So I have delta t being equals to minus 11.92 divided by minus 9.8. So, okay, let me go ahead and put that in my calculator. So minus 11.92 divided by minus 9.8, 1.22. So delta t is equals to 1.22 seconds. That is 3.3.2. Yeah, let me just verify that point P is our maximum height. I don't want to miss anything. So yeah, point P, it is indeed our maximum height. Let's move to 3.4. 3.4 is a breath of fresh air, if I can say so. Yeah, I was not looking forward to having to sketch a graph. I was not looking forward to that. So now that I have a graph and I just have to identify the points, I'm quite a fan. I didn't want to sketch a graph. Let me hear the stories, okay? The velocity time graph for the motion of the ball from the instant it is projected upwards from the top edge of the building until the time it reaches point P is shown below. Write down the numerical values indicated by each of the following. So 3.4.1, we have, let me just write that down. 3.4.1, we have K. So what is K? So let's take a look at L first. L is at t is equals to 0. So this is the velocity at which our object is projected upwards. We have the value of that. So let's just go ahead and write that first. So this is 3.4.1 we're looking for K. In 3.4.2 we're looking for L. L is 10.74. That is the velocity at which the object is projected upwards. Okay, and then here we have V is equals to 0, maximum height. We strike the ground at this velocity, and this is the velocity at which we leave the ground. So K is the velocity at which we leave the ground. It is given to us as 11.92. So the answer to 3.4.1 is 11.92. Okay, we are only interested on the numerical value. We don't have to put the SI unit. Right, and then T2 minus T1. Let's take a look. So T2 is our total time, the time at point P. And then let's take a look at T1. T1 is the time at which we are striking the ground. So T2 minus T1 should be the time from the ground to the maximum height, which is 1.22 seconds, like we calculated in the question above. Okay, this is quite not accurate. This is quite not accurate. I don't know if you're able to see why I'm saying that. This is the correct answer. It is the answer in the memo. I know that 100%, but it is not quite accurate. Think about it. If you get what I'm saying, if you can comprehend the idea, let me know in the comments. Let me know in the comments if you get it. What do I mean when I say this 1.22 is not quite accurate? Right, that is question 3. Let me know in the comment section which question you want me to do next. A wooden trolley of mass 2.7 kg moves to the left with a constant velocity of 3 meters per second. A bullet of mass 0.03 kg is fired horizontally from the left towards the trolley. See diagram A. Okay, we can see in the diagram that the trolley is moving to the west and the bullet is moving to the east. Let's carry on and hear the stories. The bullet strikes the trolley and comes to rest inside the trolley in 0.02 seconds. Okay, the average net force exerted by the trolley on the bullet during this time is 591 newtons. So the net force exerted by the trolley on the bullet is 591 newtons. Right. The bullet trolley combination now moves to the right. See diagram 2, as we can clearly see in diagram 2. Let's go ahead and answer the questions. The first question, 4.1, we are told that we can ignore all frictional and rotational effects, okay? Write down the magnitude and direction of the average net force that the bullet exerts on the trolley. 4.1. We are given the average net force that the trolley exerts on the bullet. Now we want the average net force that the bullet exists on the trolley. Newton's third law. So they should have the same magnitude, but in opposite directions. Okay, so the magnitude of the net force that the bullet exerts on the trolley will be 591 newtons. That is 4.1. Let's take a look at 4.2. Calculate the magnitude of the velocity with which the bullet strikes the trolley. Calculate the magnitude of the velocity with which the bullet strikes the trolley. Let's jot down the information we have. The information we have is going to guide us to the formula we need to use. So we have F, which is equals to 591 newtons. Okay, we're interested on the bullet because we want the magnitude of the velocity with which the bullet strikes the trolley. Okay, so this will be 591 newtons to the left. This is to the left. Okay, because the trolley is moving to the left. When it hits the bullet, it will apply a force to the left. So that is one thing we know. Another piece of information we have is the mass of the bullet. It is 0.03 kgs. Right. What are we looking for? The question says we must find the magnitude of the velocity with which the bullet strikes the trolley. The bullet comes to rest inside the trolley in 0.02 seconds. So we have a delta t, which is equals to 0.02 seconds, and a VF, which is equals to 0. This is when the bullet rests inside the trolley. What we are interested in is VI, the velocity at which the bullet strikes the trolley. If you take a look at our variables, you can see that they are taking us to F net is equals to the change in momentum divided by the change in time, where F net will be equals to minus 591 being equals to the mass multiplied by VF minus VI. The mass of the bullet, that is 0.03, multiplied by VF. VF is 0. What is VI? What we are interested in. Everything divided by the change in time. The change in time is 0.02. So we are going to cross multiply. If we cross multiply, we're going to have minus 591 multiplied by 0.02, which will give us minus 11.82 being equals to, okay, 0.03 multiplied by 0, that is 0. And then 0.03 multiplied by minus VI is going to be minus 0.03 VI. If we divide both sides by minus 0.03, so let me just go ahead and do that. I'm getting 394. So VI is equals to 394 meters per second, which is a realistic speed for a bullet. It makes sense. If we were getting 20 meters per second, it wouldn't make sense. But a velocity of 394 meters per second for a bullet makes sense. Okay, it's traveling just above the speed of sound in air. Let's carry on. That is 4.2. 4.3. State the principle of conservation of linear momentum in words. Well, the total linear momentum in an isolated system remains constant or is conserved. Okay, that is 4.3. Not trickery there whatsoever. It should be max we are getting. 4.3. What about 4.4? 4.4, calculate the magnitude of the velocity of the bullet trolley combination after the collision. So in 4.3, I defined the linear momentum in words. In 4.4, I'm most likely to use it. So I'm going to start by saying that the sum of the momentum before is equals to the sum of the momentum after. This formula will earn you a mark. Even if you don't say M1, V1, even if you don't do that, this formula is going to earn you a mark. Just the way it is. The sum of momentum before is equal to the sum of momentum after. So you must start with this formula. Because if you start with that one that says M1, V1, you might get it wrong. But there's no way you will get this formula wrong. It is always like this. There is no... Yeah, there's nothing you need to change. It's just always like this. Okay, now we can go ahead and take a look at our situation. We want the magnitude of the velocity of the bullet trolley combination after the collision. So initially we have the bullet, so we're going to calculate the momentum of the bullet plus the momentum of the trolley. So let me use T, and then now we're going to have the momentum of the bullet and the trolley. Okay, the momentum of the bullet before the collision is 0.03 multiplied by VI, which we just calculated above, which is 394, plus the momentum of the trolley. So the mass is 3, and no, the mass is not 3, the mass is 2.7, and the velocity is 3, but to the west or to the left. So this is going to be minus 3, being equals to the momentum of the bullet trolley system. So now we have M1 plus M2. So that is 2.7 plus 0.03 multiplied by VF, which is what you're interested in. So let me just put together all those numbers on the left-hand side and see what I get. I'm getting 3.72. So I have 3.72 being equals to 2.73 VF. Now I just need to divide both sides by 2.73. So 3.72 divided by 2.73, that is 1.36. So I have 1.36 meters per second to the right. Am I only looking for the magnitude? Right, I'm looking for the magnitude, so I don't have to write to the right or to the left. So yes, that is question 4. I've already done question 5. If you have not watched it, then click on the channel and go ahead and watch it. Tell me which question you want me to do next. Just leave a comment. I'm gonna check it out. Let's take a look. Let us conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy EKA. The horizontal distance traveled by the trolley before it comes to rest is then measured. See the diagram below, okay? So the learner is pushing the trolley until it reaches point A. After the trolley reaches point A, the learner lets go, and then the trolley moves until it comes to a stop. So the learner is taking note of the initial kinetic energy of the trolley and then measuring the distance, okay? Let's see what the first question says. 5.1. Draw a labeled free body diagram showing all the forces acting on the trolley during its motion after passing point A. You can clearly see that point A is in bold, right? So we need to take note of that. So let's take a look. It is resting on a surface. So obviously, I'm going to start with normal force. After normal force, I have the weight, okay? If it is resting on a surface, I'm going to have the normal force and I'm going to have the weight. Well, the weight is always there, regardless of whether it's hanging or it is resting on a surface. Let's look at the mark allocation. The mark allocation is 3 and not 4. So we have only one other force we are looking for, which is frictional force, okay? The object is coming to a stop because there's frictional force. In the absence of frictional force, the object is supposed to keep going until forever. The object only stops because of frictional force. So we have frictional force. That is the third force. There's no force applied after passing point A. So if you actually include force applied, then this is wrong. If you put force applied, this is wrong. You're going to get the mark for the normal, the weight, but not for the friction because you also have force applied. You're going to forfeit 1 mark if you put force applied. So just know, if you wrote force applied on the free body diagram, it is wrong. I'm sorry, but it is how it is. Let's move to 5.2. So 5.2, name the independent variable in this experiment. So the independent variable is the variable you're willingly changing, and the dependent variable is the variable you're measuring after you've made that change. In our case, we are changing the initial kinetic energy of the trolley, and then we are measuring the distance it traveled. So the independent is the initial kinetic energy. That is our independent variable. So initial kinetic energy is our independent variable. Let's go ahead and do 5.3. 5.3 states the work energy theorem in words. State the work energy theorem in words. Well, it says that work net is equals to the change in EK. In words, the net work done on an object is equals to the object's change in kinetic energy. Okay, sometimes I see people losing a mark because they just say the net work on an object is equals to the object's change in kinetic energy, but that's not how you're supposed to say it. The net work done on an object it is the net work done on the object. It is not just the network. No, it is the network done on the object. Okay, so that is 5.3. Let's do 5.4. Calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. Okay, in a case like this, in 5.3, I defined the work energy theorem. In 5.4, I'm going to use the work energy theorem, right? That is the first thing I'm going to try out. I'm not saying that it will always work, but if you define something in the question above, you should be expecting that you will need to use it in the question that follows. So let me go ahead and see if I can use the work energy theorem. Okay, so work net is equals to change in EK. Let me take a look at the information I have. I have the coefficient of kinetic friction. If I have the coefficient, obviously I can find the friction. So I have FR, of which my FR is the F net, because frictional force is the only force that is doing work on the object. Normal force and weight, they're not doing any work, right? We're going to have cos of 90 and cos of 270, which will give us 0. So the normal force and the weight, they're not doing any work on our object. So I have the frictional force. Okay. Let's see. Do I have delta X? This is what the problem solving is. Do we have delta X? That's what the problem solving is. If you come here to your diagram, you should be able to see that you are given initial kinetic energy and its corresponding distance traveled. So let me take 12 and 3, okay, because this is the point. That point we have 12 for the kinetic energy and 3 for the distance travel. So you can take that point. You can also take 18 and 4.5. You can take 6 and 1.5. Whichever point you take, it doesn't matter. But this is where the problem solving starts. This is the difficulty of the question. That's what you had to realize. Okay, so let me carry on. I can say that when my EK initial is equals to 12 joules, my delta X is equals to 3 meters. Yeah, that is correct. When my initial kinetic energy is 12 joules, my delta X is equals to 3 meters. But I also know there's something that I know. I also know the kinetic energy final, because this is the distance the object travels until it comes to rest. So the kinetic energy final is equals to 0 joules because our object is coming to rest. So let me take a look. I have the frictional force, I have EK initial, I have EK final, and delta X. I think I can go ahead and substitute. Okay. When I substitute, I'm going to have FR, which is my F net, multiplied by delta X, multiplied by cos of 180, being equals to EK final minus EK initial. Okay, so what is frictional force? Frictional force is equals to, not coefficient, but frictional force is equals to the coefficient multiplied by the normal force. What is the coefficient? Let me take a look. The coefficient is 0.18. So we have 0.18 multiplied by normal force on a horizontal surface with no force acting at an angle is going to be the mass multiplied by 9.8. So this is the frictional force. Let me just put that in my calculator real quick. When I do that, I get 1.764 m. Okay, so in place of the frictional force, I'm gonna have 1.764 m multiplied by delta x, which is 3 cos of 180. So this is minus 1, being equals to ek final, that is 0, minus ek initial, which is 12. Okay, so now I have 1.764 multiplied by 3 multiplied by minus 1. So let me put that in my calculator real quick and see what I have. I'm getting minus 5.292 m is equals to minus 12. I need to divide both sides by the coefficient of m. So when I do that, let me go ahead and do that. I'm getting 2.27 kgs. Our mass is kgs as the mass of our trolley. That is 5.4. Tell me, which question do you want me to do next? Drop a comment. Let me know in the comments. I'm already done with solving all the questions. I just want you to tell me which question I need to do next. I need to record and upload. Let me know in the comments. Is it question 10? Because I think the last question 10, was quite interesting. Let me know. 6.1.1, state the Doppler effect in words. I'm just going to leave that for you. Let's take a look at 6.1.2. Use the given information to calculate the speed of sound in air. So let's take a look at the information we have. So an ambulance is moving away from a stationary listener. So if the listener is stationary, then we have VL, the velocity of the listener, being equals to 0. Okay, the ambulance is moving away from the stationary listener with a constant velocity of 25. So we have VS, the velocity of the source, being equals to 25. Okay, the siren of the ambulance emits sound waves at a frequency of 550 hertz. So we have the frequency as emitted by the source being 550 hertz. The siren of the ambulance, okay, 550 hertz. Let's carry on. The listener detects the frequency of these sound waves to be 512.64 hertz. So the frequency as observed by the listener is 512.64 hertz. Okay, we are told that the ambulance is moving away. But even if the question didn't say that the ambulance is moving away, we would be able to deduce it from the mere fact that the frequency of the listener is less than that of the source. But anyway, stories. So V, which is the speed of sound in air, what we're interested in, we don't have that. Okay, so that is our unknown variable. Sticking to the basics, we're going to have FL, the frequency observed by the listener, being equals to V plus or minus the velocity of the listener, V plus or minus the velocity of the source, multiplied by the frequency as emitted by the source. The frequency experienced by the listener is 512.64, being equals to speed of sound in air, what we're interested in, plus or minus the velocity of the listener. The listener is stationary, so VL is equals to 0. Everything divided by V. The ambulance is moving away, so that is supposed to be plus 25 in the denominator. If it was moving towards, it would be minus 25, multiplied by the velocity, not the velocity, but the frequency of the source. That is 550. Okay, so a mark for the formula, a mark for the substitution. Usually it's 2 marks for the substitution. They find a way to somehow squeeze 2 marks for the substitution. But let's forget about that and focus on the problem solving. Okay, so there's a couple of different methods people will use in this position, but ultimately we must get to the same answer. So this is the method I'm going to use. I will divide both sides by 550. Okay, so 550 and 550 will cancel out on the right hand side, and then on the left hand side I'm gonna have 512.64 divided by 550, which is 0.9321. So I have 0.9321 being equals to V divided by V plus 25. I didn't do anything fancy here. I just divided both sides by 550. Okay, and now I want to go ahead and cross multiply. V multiplied by 0.9321 will be 0.9321 V. Okay, and now I have 0.9321 multiplied by 25. That is going to be plus 23.3018. Okay, I'm rounding off to 4 decimal places because I'm not at the final answer. At the final answer, I'm going to round off to 2 decimal places, not 1. Okay, and then V multiplied by 1, it is just a V. If I take 0.9321 V to the left hand side, to the right hand side, I'm going to have 1 minus 0.9321, which is 0.0679. So I have 23.3018 being equals to 0.0679 V. It is obvious what I'm going to do at this point. I'm going to divide both sides by the coefficient of V, which is 0.0679. Okay, if I do that, I'm getting 343.18 meters per second. I'm quite happy with this answer because this is the value we usually get. We have 343. It's always somewhere there. Okay, so it is not unusual. It is not odd. If I was getting 20 meters per second or 900 meters per second, I would be panicking. But now I have 343, which is almost the value I always get in other problems. Okay, that is 6.1.2. 6.1.3, a bit conceptual. The ambulance is now moving away from the listener with a velocity that is greater than 25. Okay, how will each of the following change? Choose from increase, decrease, or remain the same. Let's take a look. A, the speed of sound in air. The speed of sound in air will remain constant, right? The speed of sound in air is not a function of how fast the velocity of the source is, right? So this will remain the same, okay? And then B, the frequency of the sound waves emitted by the siren. If you are emitting sound waves with a frequency of 500, that is not dependent on how fast you're moving. The frequency that you're emitting is going to be 500, whether you're stationary, whether you're moving towards, whether you're moving away. So again, we have remained the same, right? So this is the remains the same. Now let's look at C, the frequency of the sound waves detected by the listener. Take a look at our equation. We had FL being equals to V divided by V plus Vs multiplied by the frequency of the source. Okay, as you can clearly see, if the velocity of the source increases, we're gonna have a way greater denominator. And then if you increase the denominator, the number as a whole is decreasing. So the frequency of the listener would decrease, right? So the answer to C is decreases. Yeah, we can clearly see that from our equation. And then 6.2.1, the spectrum of a distant star when viewed from the Earth is redshifted. Is the star moving away or towards the Earth? And 6.2.2 says that use the Doppler effect to explain the answer to question 6.2.1. Right, I'm interested on how you answered this question. So 6.2.1, is it moving away or is it moving towards? Let me know in the comment. And what reason did you give? Why are you saying it is moving away? If you said it is moving towards, why are you saying that is the case? Let me know in the comment section. Let's take a look. 7.1, describe an electric field. Well, it is the region in space, so on and so on. I know that is not the question we're interested in. We're interested in 7.3. Let's just do 7.2 first and move to 7.3. I know that is the question you're here for. Okay, so 7.2, draw the resultant electric field pattern due to charges A and B. Let's take a look at A. A is positive, B is positive, so they're going to repel. They have the same magnitude, so we're going to have something that looks like the following. They are going to repel because they are like charges. They are both positive, so the field lines should be pointing away from the charge. This arrow should be pointing away from the charge and not towards, like we would see in a negatively charged sphere. Okay, so we are supposed to have something like this. Okay, two positive charges, they're going to repel. This is how the electric field pattern is going to look like. 7.2. Taking a look at 7.3. Okay, so in 7.3, we are told that the magnitude of the net electric field pattern at point P is 27. So we have E net being equals to 27 newtons per coulomb of charge. Let's calculate the value of R. Let's take a look at our situation. Okay, my grade 10 kids can solve this question. Let me just leave it like that. Let's carry on. Okay, so we have A, which is positive. We have B, which is positive. We are given the net electric field at point P. Okay, so let's have a vector for the electric field due to A and the electric field due to B at point P. Okay, the way we do this is we always assume that at point P we have a positively charged sphere. Okay, so let's take a look at A and P. If A is positive and P is positive, that is repulsion. So P is going to be pushed to the right by A. Okay, so this is the electric field as a consequence of A. Now let's take a look at P, which is positive, and B, which is positive. Okay, we have repulsion once again. So this will be the electric field as a consequence of B at point P. As you can see, we're going to have E net being equals to EA minus EB. But we have the value of E net. E net is 27. We're going to have 27 being equals to the electric field due to A. What you want to write first is the equation. You need to write E is equals to KQ divided by R squared. There's a formula for this, so make sure that you don't forget to write that somewhere, okay? If I go ahead and substitute on that formula, I'm going to have 9 times 10 to the power 9 multiplied by the magnitude of A, which is 3 times 10 to the power minus 9, divided by the distance between P and A. It is given to us as R. So we're going to have R squared, okay, minus 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by R. But R, the distance between P and B, is 2R. So we're going to have 2R squared, okay? This will be equals to, so we have 27 being equals to 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by R squared, minus 9 times 10 to the 9 multiplied by 3 times 10 to the minus 9. Everything divided by 4R squared. Okay, so now it comes down to mathematics. Other people will use different methods, so on and so on. But ultimately, we must get to the same answer. So this is how I did it. I'm taking 1 divided by R squared as a common factor on the right hand side. Let me show you what I'm going to have. I will have 27 being equals to, open bracket, 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 1, minus 9 times 10 to the minus 9 multiplied by, not to the minus 9, but to the plus 9, okay? I think I made the same mistake there. To the power 9, to the power 9, multiplied by 3 times 10 to the minus 9, divided by 4, okay? I'm taking 1 divided by r squared as a common factor. So I can go ahead and put this in my calculator, okay? So I will have 27 being equals to. So let me just go ahead and put that in my calculator once more. So I have 3, not 3, but 9. 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 1 minus 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 4. Okay, if I put that in my calculator, I get 20.25 multiplied by 1 divided by r squared. Okay, so this is just 27 being equals to 20.25 divided by r squared. If I go ahead and cross multiply, I'm going to get 27 r squared being equals to 20.25. So r squared is equals to 20.25 divided by 27. And that is 0.75. So I'm taking square roots on both sides. Okay, let me go ahead and do that. If I do that, I get 0.87 meters. And when I substitute it back into my equation for E net, I get 27. So I'm quite convinced that R is indeed equals to 0.87. So that is 7.3. That is 7.3. Let me know in the comments if you got a different answer, but it is probably wrong. Yeah, it is probably wrong. Maybe I'm wrong, but I don't know. It's probably wrong. I think R is 0.87 meters. Just let me know in the comments if you get the same thing. Oh, there's something I'm missing here. Okay. 7.4. Calculate the magnitude of the net electrostatic force that an electron will experience if placed at P. So we know that E is equals to F divided by Q. Okay. So if we want to find F and we have E, we just see F is equals to E multiplied by Q. The net electric field is 27. Okay, so we have 27 multiplied by Q. Q being the charge of an electron. So we are only interested in the magnitude. So we're going to have 1.6 times 10 to the minus 19. I think if you put that in your calculator, you should get 4.32 times 10 to the minus 18 newtons. Right, let me know in the comments if we got the same answer. I'm just putting it in my calculator once more to verify. 4.32 times 10 to the minus 18 newtons. So there we go. Question 7. Did we get the same answer? Let me know. I'm quite sure that a lot of people were not even able to calculate the total external resistance of the circuit. Let me show you why. We're going to skip 8.1, obviously. It is just Ohm's law. V is equals to I multiplied by R. Let's take a look at 8.2.1 instead. So we're looking for the total external resistance of the circuit. Okay, we know fully well that R external is equals to RP plus RS. Let's take a look at RS first because it is easier to calculate the resistance in series. You just add all those resistors up. If you take a look at our setup, you should realize fairly quick that we have no resistance in series. RS is equals to 0 ohms in the grand scheme of things. You're gonna see why I'm saying in the grand scheme of things. Okay, if you are not very fluent with electric circuits, then we need to do this first. This is the negative terminal. This is the positive terminal. The current flows from positive to negative. So it is going to flow in the following fashion. We're going to have something like this. But at this point, the current splits, right? A proportion of the current goes down this path while the other proportion of the current goes down this path. Okay? So the total resistance on this path is in parallel with the total resistance on this path. Okay, but it is a bit deeper than that because on the upper path we have R1 and R2, which are also in parallel. So we need to find the effective resistance of R1 and R2 first, okay? So RP will be equals to R1 multiplied by R2 divided by R1 plus R2, okay? So we have 10 multiplied by 10, 100 divided by 10 plus 10, 20. 100 divided by 20 is 5 ohms, okay? So the effective resistance of these two resistors is actually 5 ohms, right? So that tells us that the total resistance on the upper path is 5 ohms plus 10 ohms, which is 15 ohms, okay? So if we want to calculate RP for this path and this path together, we're going to have RP for the entire circuit. We're going to have RP being equals to R1 multiplied by R2. R1 is the total resistance on the upper path, which is 5 plus 10, multiplied by the total resistance on the lower path, which is 15 ohms, okay? Everything divided by R1 plus R2. So that is 5 plus 10 plus 15. On the numerator, we have 15 multiplied by 15. On the denominator, we have 15 plus 15. RP will be equals to 7.5 ohm. Okay, so this is the total external resistance of our circuit. It is 7.5 ohms. Let's move to 8.2.2. Yeah, this situation where you have parallel on a path that is parallel, it is not so common, but you need to know how to take care of that. You first have to calculate the effective resistance of R1 and R2. Let's go ahead and take a look at 8.2.2. In 8.2.2, we want the reading on the ammeter. As you can clearly see, the ammeter is experiencing current that is not divided. So basically, we're looking for I total, okay? So I total is what we're interested in. We have R external, which is equals to 7.5 ohms. We have R internal, which is 0.5. We have EMF, which is equals to 12. It will be obvious the equation we need to use, okay? EMF is equals to I total multiplied by R external plus R internal. EMF is 12. I total is what we're interested in. R external 7.5, R internal 0.5. Okay, so 12 is equals to IT multiplied by 8. So IT will be equals to 12 divided by 8. That should be 1 point something, 1.5 ampere. So there we go. We have our current. 8.2.3. What's the mark allocation? 4 marks. Okay. 8.2.3. We're interested in the power dissipated by R3. Okay. So R3, the potential difference across R3 is VP, because on that path we only have R3. If we calculate VP, then we can say that the power dissipated by resistor R3 will be equals to V squared divided by R, okay? So let's go ahead and find VP. VP is IT multiplied by RT. IT, that is 1.5. RT, the total resistance in parallel, that is 7.5. We know fully well that RT is not RT, but RP, right? That's supposed to be RP. VP is equals to IT multiplied by RP, okay? So 1.5 multiplied by 7.5, that is 11.25 volts. So we have VP. We can go ahead and calculate the power. The power is going to be 11.25 squared divided by the resistance, which is 15, okay? Let me go ahead and put that in my calculator. So 11.25 squared divided by 15 is 8.44 watts, right? So there we go. We have our power. The power is 8.44 watts. 8.3, 8.3.1. Switch S is now opened. Okay, so let's go ahead and open switch S. if we open switch S, this resistor R3 is no longer taking part in our circuit. So that other path is non-existent, basically. Okay, all the current is flowing through this path, right? It's not gonna divide at this point anymore. Yeah, we're gonna have something like that. What does our equation say? If the resistance of the light bulb remains constant, how will the brightness of the light bulb be affected? Choose from increase, decrease, or remain the same. Explain the answer to question 8.3.1. Is it increasing, decreasing, or remaining the same? Let me know in the comment section. I'm going to check the comments after an hour, and then I'm going to reply with the correct answer. So make sure that you come back here after an hour and check 8.3.2. This is 4 marks up for grabs. Did you get this 4 marks or did you lose it? Come back after an hour and find out. In the meanwhile, you can let me know what your answer is and why you think so. As you can clearly see, this is a split ring and not a slip ring. So the answer to 9.1.1, we have split ring. Okay, A is a split ring and not slip. Okay, 9.1.2, state the energy conversion that takes place in the motor. So for every motor, we have electrical energy to mechanical energy, right? We have a power source here that is providing us with electrical energy, and we convert that electrical to mechanical. Right? That's what you were supposed to write, electrical to mechanical, right? There's no other possible solution here. We have electrical energy to mechanical energy. I do see electrical to kinetic energy once in a while, but for the most part, electrical energy to mechanical energy. Okay, 9.1.3, in which direction will the coil rotate? Choose from clockwise or anti-clockwise. Okay, well, explaining this will be very difficult because you cannot see my hand, obviously. This is a motor. With a motor, we use the left hand, okay? So your index finger will point from north to south. Your middle finger is the direction of the current, and your thumb is the force or the rotation of the coil, okay? If you place your left hand on that part of the coil, and then with your index pointing from north to south, and with your middle finger showing the direction of the current, then your thumb is going to show you the direction of the coil at that part. Okay, so we have the positive terminal and the negative terminal. So the current is going to be flowing in this fashion. Okay, as you can clearly see on the part we're interested in, the current is going down. So you're supposed to twist your hand such that your index is pointing from north to south, and then your middle finger is following the current. If you do that, then this part is going to be going down, right? And if that part is going down, you can clearly see that we have a clockwise rotation. That is the answer to 9.1.3. It is unfortunate I cannot demonstrate it. Yeah, as you cannot see my hand. But practice that and wrap your head around it. 9.1.4. So 9.1.4, state 2 changes that can be made to the motor for the coil to rotate faster. Okay, I can increase the voltage, increase the voltage. If you increase the voltage, the coil will go faster. So that's one of the things you can do. I want you guys to tell me what reasons you gave. I'm saying I'm going to increase the voltage. What did you say in the exam? Let me know in the comments. I'll be checking it out. Okay, that is 9.1.4. Let's take a look at 9.2. VRMS, IRMS, so on and so on. We know what you expect. The circuit diagram below shows an electric kettle and a toaster connected to an AC source with an RMS voltage of 220 volts. Okay. The ammeter connecting wires and switches S1 and S2 have negligible resistance. Right. 9.2.1, we're supposed to define the term root mean square current. I'm going to leave that one for you. Let's do 9.2.2. 9.2.2, when switch S1 is closed and switch S2 is open, the maximum current, so I max, is equals to 3.6 ampere. Calculate the root mean square current in the circuit. Okay, so we're gonna have IRMS being equals to I max divided by square root of 2. I max 3.6 divided by square root of 2. So what should we get? I'm getting 2.55 ampere as my answer to 9.2.2. 9.2.3, on the other hand, when switch S1 is open and switch S2 is closed, the root mean square current in the circuit is 2.62 ampere. So now we have IRMS, which is 2.62 ampere. Calculate the energy consumed by the toaster in 2 minutes. So we want the energy. The energy is equals to the power multiplied by the time. Okay, so the power can take different forms, right? We can have V squared divided by R, I squared multiplied by R. So let's decide on which formula we're going to use to calculate the power. Well, we have IRMS is equals to 2.62. So now we need V or R in order to calculate the power. We have the VRMS. We are given the VRMS of the source. Okay, it is said to be 220. So we can just go ahead and find the power by saying VRMS multiplied by IRMS. Okay, obviously you can find the resistance first, which is sort of wasting your time because you don't have to do that. But if you do it, there is no problem. Okay, so we can find the power using that. And then the time, we have 2 minutes, which is just 120 seconds. Okay, so the energy consumed will be equals to the power, which is 220, our VRMS, multiplied by the current, which is 2.62, multiplied by the time, which is 120. Okay, I have the answer, but I have to put it in my calculator again and make sure. Okay, this is 69,168 joules. Okay, energy is in joules and not watts. Let's take a look. We have two spheres, A and B. They're made of pure zinc and they are at rest 0.1 meters apart on a wooden table. Sphere A is negatively charged and is free to move on the table, while sphere B is uncharged and fixed to the table, as shown in the diagram below. Okay, let's hear the stories. High intensity ultraviolet light of frequency 2.8 times 10 to the power 16 Hz is now shown onto sphere B. The work function of zinc is 6.63 times 10 to the minus 19 joules. Okay, let's carry on. 10.1.1, define the term work function of a metal. That is the minimum amount of energy required by a certain metal for electrons to be ejected or to be emitted from its metal surface, okay, right, that is work function. 10.1.2, explain using a suitable calculation why the ultraviolet light shown on sphere B will eject electrons from its surface. So we are given the work function, right, and the frequency that is shown. There's two ways you can explain using a suitable calculation why the ultraviolet light is suitable. Okay, yeah, there's two ways you can do that. You can convert the work function to the threshold frequency, and then you can compare threshold frequency with the frequency that is shown. The other way of doing it, you can use this frequency that is shown to find the energy that will be incident on the metal surface and compare the energy to the work function. One between the two ways. So our work function is equals to 6.63 times 10 to the minus 19 joules. Let me calculate the energy of the frequency that is being shown on the metal. Okay, I'm choosing to take that route. You can take the other route, which will conclude in the same fashion. So if I take this route, I'm going to have Planck's constant multiplied with the frequency. Planck's constant 6.63 times 10 to the minus 34 multiplied by the frequency that is shown. What is the frequency that is shown? 2.8 times 10 to the 16 hertz. So let me put that in my calculator. 6.63 times 10 to the minus 34 multiplied by 2.8 times 10 to the power 16. This is 1.86 times 10 to the minus 17 joules. Okay, clearly it is easy to see that 1.86 times 10 to the minus 17 joules is greater than 6.63 times 10 to the minus 19 joules. Okay, minus 17 is greater than minus 19. We know that for sure. Okay, so the energy of the light that is being shown on the metal is greater than the threshold frequency. So obviously electrons are going to be emitted. They're going to be ejected from the metal surface. So this is one way you can show that indeed the electrons are going to be emitted. Okay, 10.1.2. Let's take a look at 10.1.3, the interesting question. Okay, it was the first time I'm coming across a question like this. It's really interesting, right? But it's not difficult. I don't know why the mark allocation is 6 marks. It's not difficult at all, but it is interesting. Okay, so sphere A carries a charge of minus 5.4 times 10 to the minus 6 coulombs and requires a minimum force of 0.027 newtons to move from rest. So we have the force. Okay, the force is equals to 0.027 newtons. The charge on A is 5.4 times 10 to the minus 6. I'm forgetting about the sign. I'm just focusing on the magnitude. Okay, the question is saying, let's calculate the minimum number of photons of ultraviolet light that must strike sphere B, which will cause sphere A to move from its rest position. Okay, we have to go back to the basics. You need to understand that one photon can emit only one electron. Okay, so if we calculate the number of electrons that are being emitted on the sphere, then we can use that to calculate the number of photons. Basically, the number of electrons is equal to the number of photons. So we are actually supposed to just find the number of electrons. The number of electrons will be the number of photons. So let's go ahead and do that. Okay, so we will use F is equals to K Q1 Q2 divided by R squared. Okay, we have the electrostatic force. We have two charges that are attracting each other or repelling. I don't know in which direction they're moving. Okay, if electrons are being emitted from the sphere, then it will become positively charged. Okay, so they are attracting each other with a force of 0.027 newtons. I have Q1 or QA, which is 5.4 times 10 to the minus 6. I can go ahead and find Q2 because K is a constant and I have R. After finding Q2, then I'm going to calculate the number of electrons on Q2. Okay, let me go ahead and do that. The electrostatic force 0.027, K 9 times 10 to the 9, Q1 5.4 times 10 to the minus 6 multiplied by Q2. Everything divided by R squared. So R squared will be 0.1 squared. If we cross multiply, we're going to get, so 0.027 multiplied by 0.1 squared, I'm getting 2.7 times 10 to the minus 4, being equals to 9 times 10 to the power 9 multiplied by 5.4 times 10 to the minus 6 I'm getting 4.86 times 10 to the minus 4 multiplied by Q2. So it's obvious what I need to do. I need to divide both sides by the coefficient of, this is to the power 4 and not to the power minus 4. This is to the power 4. So let me just go ahead and change that. So we have to the power 4. Okay. So now I just need to divide both sides by 4.86 times 10 to the power 4. So what is 2.7 times 10 to the power minus 4 divided by 4.86 times 10 to the power 4? Okay, I'm getting Q2 is equals to 5.5556 times 10 to the minus 19 coulombs. So now I have the charge of Q2. I can go ahead and calculate the number of electrons that were emitted, okay? Of which the number of electrons that are emitted will give me the number of photons. So the number of electrons is equals to the charge divided by the charge of an electron. So we're going to have 5.5556 times 10 to the minus 9 divided by 1.6. Okay, 1.6 times 10 to the minus 19. That is the charge of an electron. Okay, so let me put this in my calculator. Divided by 1.6 times 10 to the minus 19, I'm getting 3.4723. Okay, 2 decimal places because this is my final answer. 3.47 times 10 to the power 10 electrons, which is the number of photons. Okay, so I think you would also need to conclude that the number of photons is equal to the number of electrons, which is 3.4723 times 10 to the power 10.